Hello all. In this video we'll see how to interface LCD with 8051. We'll see both the 8-bit and 4-bit mode. First let's start with the 8-bit mode. Here the port register P1 is used for data bus, and two of the port pins of P2 is used for control. This is the development board we will be using in this project, and the AVR dude is connected to the ISP connector. LCD can be plugged to the end Berg sticks. To the inner pins, let us do the connection first. We'll be using this type of 8-way jumper wire for connecting the data bus. Data bus we are using is port 1. So port 1.7 pin should go to D7 and port P 1.0 to go to D0. So note the direction and plug it correctly. And enable pin EN should go to P2.1, port pin P2.1. And next is the read write pin. It will be grounded permanently, so we are going to use it in write mode only LCD, so we can directly connect it to ground RW pin. And the next pin RS control pin goes to P2.0. so this is the connection. Now let us plug in the LCD. LCD has got a female connector. We can easily plug it onto the Berg stick. Now the power is on. Now let us see the coding. Open the Keil window, project, new microvision project. You should have created a folder for this LCD already, and inside this folder save the project by providing a name. Next, select the IC as AT89S52. Click on yes. Now the project has been created. Right click on target to set the options. Change the crystal frequency to 11.0592. Then only the delay will work perfectly. And then click on the output tab and put a tick mark against create a hex file. This is also very important, otherwise your hex file will not be created. Now under the source group, right click and then add new item and select the C file. Provide a name to the C file and click on OK. Now the editor window will open. Here you have to write your C code. Before that, let us see the LCD we are going to use here. It is 16 by 2 LCD. It has got 2 rows, 0 and 1, and 16 columns. The first row, first column is address is 0x80. Second one is 0xC0. And there are 8 data pins, D7 to D0. 8 data bits, and then 3 control pins. Enable EN, RW, read write, and register select RS. 3 control pins are there. Next is the contrast pin, where you will connect a potentiometer to control the contrast of the LCD, and VCC and ground. VCC is 5 volt, and backlight plus and minus for lighting up the back light. Now the control pin RS is register select. Suppose we are giving high to register select, then data register will be selected. And if you are giving low, ground to the RX, command register will be selected. So whatever data you place it on the data bus, it will act according to the RS, whether it is command or data. There is a list of commands. You can get it from the data sheet. The commands are in hex notation. 0x01 means clear display, 0x80 means cursor home, and there is a list of commands. For example, suppose you are placing 0x80 on data bus and make RS equal to 0. This makes it as command, and cursor will move to the first row, first position. Same way C0 will move to the second row, first position. And next is the read write pin RW. Suppose if this pin is 0, LCD will go to the write mode. Generally we write on LCD, so we will permanently connect this to 0. For reading means reading like busy flag, that we are not doing in this, so permanently we'll connect to 0. Next is the enable pin. it is the pulse. Suppose you are placing some data or command on data bus, it will go to LCD only after giving enable pulse, that is high to low. Now let us see the C code, how to create the C code in detail for 8-bit mode of LCD interfacing. To start with, include reg52.h, and then we have to define the port pin. We are using port pin P1 for data bus, so we'll provide a name, any name we can give. We'll provide a name as data bus and define P1 as the port pin where we place data or command. And then we use 2 more pins for RS and enable. RS is connected to P2.0 and enable is connected to P2.1. That we'll declare using the S bit data declaration. S bit RS equal to P2 caret 0 and enable EN equal to P2 caret 1. Next is the void main function. Inside this there is a while loop. While loop here we are not going to use, but it should be there. Next is the function declarations. First function is the delay underscore ms. This name is given by you can give any name. We will provide a name as delay underscore ms. First we have to declare the functions and then we'll write the code for the function. Declaration of the function ends with semicolon, and writing code will be under the braces, and there is no semicolon in this delay underscore ms function. So we'll be using 2 unsigned integers I and j, and we'll be using a nested for loop. First for loop I will take the parameter which we are giving as millisecond, and the second parameter is j less than 120 we are using, so that 1 millisecond delay is created. And next function declaration is lcd underscore write command. This takes a parameter unsigned char and we'll name it as cmd, that is for command. You can give any name, we are giving a name cmd. Now let us write the code for this function. lcd underscore write command. Here data bus equal to cmd, that is whatever command you are giving will be placed on the data bus, which is P1 here. So this 8 bits will be placed on the port P1, and then we make the RS act as 0. RS, that is the register select pin, will be made as 0 to select the command register. Next we have to provide the enable pulse. After selecting the command register, we have to give the enable pulse. Initially enable, that is make it as high, the P2.1 we are using, make it as high, and then a small delay and make it as low. This pulse will trigger, and the command we placed on the data bus will be taken to the LCD memory. And next we will create the lcd underscore write data. This is the next function declaration. First we will declare the function on the top using void lcd underscore write data, and it takes parameter unsigned char dat. We'll be using the name dat for data, and we'll write the code for this function lcd underscore write data. It is same as write command. We'll place the data on the data bus equal to dat. Whatever data we place and call the function will be placed on the port P1, and we make the register select pin as 1. This will select the data register. RS equal to 1 will select the data register, and then we give the trigger pulse en equal to 1, and after a delay en equal to low. Let us give a small delay, millisecond, 1 millisecond. So this is LCD underscore write data function. Next is the display string function. Before that, under the void main, we'll give the function LCD underscore init. So this is to initialize the LCD underscore init. We'll declare this function in the function declaration on top, void LCD underscore init. So this function will be called first, so we'll provide it in the first declaration on the top. Cut and paste to the top below the S-bit declaration. Now the code for LCD underscore init. Here the initialization is used by using the write command, LCD underscore write command, and passing on the hex values. 0x08 will make 2 lines, 5x7 matrix size and 8-bit mode. That is 0x08, and then we'll be using 0x0e, 0x01 and 0x06 and 0x80. 0x80 will that is for cursor home. First let us pass on the parameter 0x38 to the LCD underscore write command. This will make this will declare it as 8-bit mode, 2 lines, and character size is 5x7. Next, LCD underscore write command, pass on the parameter 0x0e. This is for display on and cursor on. The third one is LCD underscore write command 0x01, that is to clear the LCD. And the fourth one is 0x06, that is to for cursor shift to right. And finally 0x80, that is cursor home. That is first line, first position, that is 0x80. And finally we'll provide a delay of 100 millisecond. This is the void LCD underscore init function that will be called first under the void main function. For easy understanding in the code, let us define the 0x80 and 0xC0 as line 1 and line 2 in the code. This is declared using hash define. Hash define line 1 for 0x80 and hash define line 2 0xC0 for the second line. So inside the code, instead of 0x80 we can use line 1, and instead of 0xC0 we can use line 2. Next function declaration is LCD underscore display string. This is used to display the characters on the LCD, and the parameter is unsigned char, and we use the pointer variable, pointer string underscore ptr. Now let us see the code for this function. Void LCD underscore display string and unsigned char, pointer string underscore ptr. So here we use while loop to check whether the character is still available. That is, it will check until null, and then using LCD underscore write data, it will pass on 1 by 1 character. So the pointer will be incremented using plus plus, and then the character will be sent 1 by 1 to the LCD for display. So this is easily achieved using the pointer variable. Notice the usage of star asterisk for the pointer variable. Next we'll use the function declaration LCD underscore clear. This is just for a reset. Here we use 0x01 command for reset type, that is clear display. Everything will be cleared on the display. So pass on the hex 0x01 to LCD underscore write command function. Then the cursor will move to home using the line 1, that is we are passing 0x80. hex to LCD underscore write command. The cursor will go to the home. This is the LCD underscore clear function. Now all functions we have declared. Save this file, and before that, under the void main function, we have to feed in the string we are going to display on the LCD. For that, we use the LCD underscore display string. After LCD underscore init, we use the LCD underscore display string and pass on the first string to be displayed on first row, and to go to the second row, use the LCD underscore write command, and then line 2, that is 0xC0 is the line 2. The cursor will move to the line 2, and we use again the LCD underscore display string to display the second string of characters. After that, while inside the while repeated loop, nothing is there, so put a semicolon there, save this, and then build the hex file. Now it is showing 0 errors and 1 warning. We can omit the warning, but we'll see why this warning is there. That is void LCD underscore clear. We have defined the function, but we are not using in the code. So let us use this inside the void main, void underscore that is LCD underscore clear. Now let us rebuild it. You can see no errors, no warnings. Now it is ready. Let us open the ProgISP software and then click on File, Load Flash, and go to the LCD underscore 8.hex file we created using Kale. Select it is under the objects folder of your project folder. Select that hex file and then click on auto. Now automatically the chip is erased, 89S2 flash memory is erased, and the hex file is loaded and then finally verified. You can see the green bar at the bottom of the ProgISP, and finally it shows ready. You can see in the AVR dude where the red LED is glowing while the hex file is being uploaded, and once the red LED is off, you can see the display on the LCD, the first string on the first row and the second string on the second row. You can adjust the contrast potentiometer if you do not see anything. So the 8-bit C code we have seen. Next we'll see how to create the 4-bit mode. Now copy this 8-bit code we have created, and then from project, click on new project, provide a folder, new folder for LCD 4-bit, and then create a new file that is a project name for this, and select the ICS 8089S52 as we have done before, and the target settings, change the crystal frequency, and the output you put a tick mark against create hex, and the source file, right click and add the C file, provide a name LCD underscore 4-bit and click on OK. Now here in the code window, paste the code that you copied from 8-bit mode. Now let us modify this to work as 4-bit. So in the connections, we'll be using D4 to D7 only. D0 to D3 is not used. Only the higher nibble used, D4 to D7, MSB side. So the first thing you have to change is the under void LCD underscore init, that is 0x38 to be changed to 0x28. This is for declaring as 4-bit mode. 38 is for 8-bit mode, and 28 is for 2 lines 5x7 matrix 4-bit mode. And along with that, you have to previously provide 0x02, that is the home back. The LCD cursor will go to home back. That 0x02 also to be sent using LCD underscore write command. Otherwise this will not work. 0x02 first and then 0x28. This will make declare it as 4-bit mode. and let us modify the void lcd underscore write command. So in this write command, data bus, that is the command you are sending, is placed on the data bus port P1, but here we are using only the 4 bits, so the command you placed on that will be, and you will use the AND function with hex F0. So this will mask the lower nibble 4 bits, and it will take only the higher nibbles. By ANDing with hex F0, the command you are placing, only the higher nibble will be taken, and the rest of the code is same, rs equal to 0 and enable pulse. And again you copy this and paste it, so that we'll mask the upper nibble. For this you have to shift the command to left shift by 4 bits, and then again AND it with F0. So now you masked both the upper nibble as well as the lower nibble. So 8 bits you are taken out. So next lcd underscore write data, we'll do the same thing. First we will place the data on the data bus and AND it with F0, and again we'll shift left by 4 bits and then AND it with F0. So let us see, for example, at the command we are using 0x28. In binary it is 0010 1000, and AND it with F0. Hex F0 is 1111 and all zeros. So if we AND this, we'll get 0010. That is the upper nibble is separated. Upper nibble means 4 bit. Upper nibble is separated and lower nibble is masked. And let us shift this by 4 bits to left. That is pushing 4 bits to left. And again that is shift left 4 times. And again AND it with F0, hex F0. That is 1111 and 0000. AND it with F0. You get the lower nibble separate. So upper nibble is masked now. Lower nibble is separated. So this is the basic behind this code, 4-bit code. Now let us do the connection. Remove the 8-bit connection from port 1. We'll be using D4 to D7 only. So the command pins will be remaining as it is, RW, RS and enable pins. For data bits, D7 and D4 is used. D7 goes to P1.7 and D4 goes to P1.4. So only the 4 bits are used here. And the P1.0 to P1.3 is not used. The command pins are left as it is as we used for 8-bit. Now upload the code, and once the code is uploaded, you can see the result on the display. So it works as like 8-bit but a bit slower. Next we will create a header file for this LCD 4-bit so that it can be easily used with all your other projects. Now cut all the function definitions, and from file create a new file, paste the file definitions here. All define S-bit definitions and function definitions, you paste it here. Go back to the main file and cut all the functions we created. That is all the lcd underscore write command, write data, all functions you cut and paste it to the new file. Now save this file as .h file. You have to provide extension .h. Let us give a name lcd underscore 8-bit .h, as we are modifying the 8-bit code. And the main file has got only the void main function and while function. Here now we use hash include the new header file we created. Now save this file and then click on build. We can easily build the project. Thank you for watching.